This tutorial describes the addition of electric and magnetic fields to the workspace. This is the workspace here, which could contain any number of molecules, and these applied fields apply to each molecule in the workspace, or to the whole workspace. So let's get a molecule. Let's build one out of lithium. Put down a lithium atom. Build that, and we have lithium hydride, which has a strong dipole moment. This molecule is along the y-axis at the moment, and this is the x-axis is horizontal. So we go up and we say apply or set finite field. If we're going to put a magnetic field on, we can only do this with the TNDO methodology. That's the only method that currently has the ability to incorporate magnetic fields. However, electric fields can be added to any quantum mechanical method, semi-empirical, ab initio, density functional theory. So let's take an electric field, 0.001 say, atomic units, put it along the x-axis, and now we have an electric field here. If we choose a method, let's choose a semi-empirical method, AM1 is fine. Let's now do an optimization and see what happens. Just turn on the optimizer. It didn't have the optimum bond length, so it shrunk that a little bit, and now it's optimizing. And when it optimizes, it ends up being along the x-axis because that's where the electric field is, and the dipole moment wants to be parallel to the electric field. So that's an optimization in an electric field. That the bond length will probably be slightly different than it would be without the electric field, but nevertheless, that's an optimized molecule. Let's rebuild this and put it back in the x-axis here. Let's now optimize this without the electric field. And then let's turn on the electric field. Again, 0.001. And let's do molecular dynamics and see what happens. Turn on molecular dynamics. Restart here means start with the existing velocities, which are basically zero. But if we proceed, what happens? Actually, it starts rotating because there is a force wanting to align it with the x-axis, but it doesn't stop there. It keeps going. Basically, we have kinetic and potential energy. When it's aligned with the x-axis, it has the minimum potential energy, but it actually had the maximum kinetic energy because we're doing molecular dynamics here. And so this is actually a pendulum that will go back and forth continually. We ran out of time here. We had 0.3 picoseconds, but basically this is the minimum potential energy, but the maximum kinetic energy. When we started with it aligned along the x-axis, it had potential energy because it was not in the optimum position according to the electric field. Anyway, that's how you can apply an electric field to the workspace. One can actually calculate polarizabilities manually if you wanted to by looking at the dipole moment that's induced in this electric field. Alternatively, we can forget about the electric field, turn it off, and build this again and calculate the polarizabilities by another method here, by just turning on and saying to calculate the polarizabilities. That also applies an electric field, which is a different electric field, but is specifically for the polarizabilities, and we could actually calculate the polarizability in an applied electric field. This electric field is a finite field that is used in the perturbation methodology to calculate polarizabilities. If we do that and ask to calculate polarizabilities, we have to do a single point calculation. A single point calculation says it's going to do 6 of them actually to calculate the polarizability. So it does these single point calculations and then generates the polarizability. We can see that by going up and asking to see the properties, and here's the polarizability, or here's the tensor that it computed for the polarizability tensor. So one can apply external electric fields and or calculate the polarizabilities as a separate operation.